We are delighted to have our next speakers, Xiongfeng Ma from Tsinghua University in Beijing. So he will speak to us about mode-pairing quantum key distribution. Before you start, let me introduce you briefly. Xiongfeng Ma is currently an associate professor at Tsinghua University. His main research interest lies in quantum information and quantum optics, particularly in quantum cryptography and quantum foundation. After obtaining his bachelor degree at Peking University in 2003, Xiongfeng attended the University of Toronto for his PhD degree. From 2008 to 2011, he did his postdoc and visiting positions at the University of Waterloo, the University of Toronto, and the University of Leeds in UK. In 2012, Xiongfeng joined Tsinghua University in Beijing. It's very nice to have you, so the floor is yours.
Okay. Can you hear me? Can you hear me?
Yes. Let me remind you that the talk is 30 minutes, 25 minutes for talk and 5 minutes for questions. And
okay,
I will
thanks.
remind you three minutes before that. Thank you.
Okay. All right, thanks. Okay, first of all, I'd like to thank the speakers to give me this opportunity to introduce some of our recent works on mode-pairing quantum key distribution. So this is a joint work with my students, Pei Zheng, who is now a postdoc at the Chicago University of Chicago, and Wei Jie, and he's now at Harvard. Hong Yi, he's now at the faculty at the CAS. All right, so I will give a brief introduction about the quantum key distribution and the intuition for security. Then I will quickly talk about the measurement device independent quantum key distribution, which is the one of the most hottest topic in the field for the last 10 years. Then I will talk about the quantum key distribution and its experimental realization. Finally, I will draw a conclusion. Introduction. So we know that the problem with the conventional cryptography is that the foundation, the mathematical foundation, is unclear. So it's unproven. So basically, it's like we have to assume that what kind of computational power the eavesdropper, the hacker, has. So, but with the development of the computers, especially with the quantum computers, such kind of assumption could be violated in the future. And then we part of the cryptography we need to replace with the so-called quantum cryptography. Then we based on the foundation of the quantum mechanics. But here I need to emphasize that the quantum communication cannot replace with the classical communication, at least not now. Quantum cryptography cannot replace the current cryptography means. So in a way, it's currently what we can provide in the quantum cryptography. It's just part of the cryptography. Most of the rest of the part is still the conventional cryptography. So in the quantum cryptography, our target is we call the information theoretical security, or sometimes we call the long time ago we call it unconditional security and the absolute security. So that means that we do not put any assumption on the computational powers of the hacker. But from time to time, we hear that we can have we hack the quantum system. So what's the difference? The key point is that what we offer here, what we prove here, is really let me call for the cursor. Yeah, now we have a pointer. So in what we have in the research, what we prove is that in theory we prove that those kind of security, but when we talk about the practical systems, we have lots of practical issues coming up. Those we call the practical security. There's a big difference between theoretical security and the practical security, because that's the instruments might not be well built. So basically, it's like when we say a system is secure, it's based on the assumption that your instruments, your components is built according to my security model. But if there's a mismatch between these two, then we might have some loopholes. There might be a kind of malicious backdoors. Quick review. So we know that the first QKD protocol is proposed by Charles Bennett and Joe Broussard published in 1984. And then we have a bunch of other protocols. And then there's also another type of protocol. It's called the entanglement-based protocol. The security proof is originally given by Rocha, Shopler-Skill. There's lots of developments in the last 2 decades. Okay, let me quickly introduce the we call the entanglement-based protocol, DBM92. So we have an entanglement source in the middle, and then let's say this source is can be prepared by Alice or can be prepared by Eve, Uncharted Source, and then 1 qubit go to Alice, 1 qubit go to Bob. Ideally, Alice Bob will share after this distribution. Ideally, Alice Bob will share a perfect EPR pair 00 plus 11. Then what they can do, Alice and Bob, they perform Z measurement. Alice performs Z measurement, Bob performs Z measurement, and then they always get the same result, 00, both are 0 or both are 1. Similarly, they can perform X measurement. They will both get plus plus, either both are plus or both minus. So what they can do, they can with half probability get 0, half probability get 1. Okay. So what's the idea of the low-Charles security proof? Is that if Alice and Bob get 1 qubit Alice, 1 qubit Bob, so we can choose we call the barrel basis. Okay, 00 plus minus 11, 01 plus 1 minus 10. And then these 2 qubits can be we can express these 2 qubits into these bases. And then their objective is that to get 00 plus 11. So this is their objective. But the channel and also the devices inevitably will introduce errors. So you might have some bit errors. So when we say bit error, we have a bit flip error. So 00 plus 11 becomes 01 plus 10. Or we might have phase errors, 00 minus 11. So 00 minus 11 equals to plus minus plus minus plus. And sometimes you can have both bits and the phase errors, like 0, 1, minus 10. Okay, so whichever basis you measure, you will get an error. So there are 4 cases: no error, bit error, phase error, both errors. Okay, the key idea of the low-Charles security proof is actually from today's point of view, it's rather straightforward. It's just you perform quantum error correction, and then if the error is small enough, you can perform quantum error correction to reach almost pure EPR pairs 00 plus 11. Okay, so this is objective. Oh, that's your objective. Okay, once you get this 00 plus 11, this n qubit EPR pairs, and EPR pairs, then you can, Alice Bob can measure Z bases, both measure Z bases. They will reach the final key. Okay, they will reach the final key. Why we do it? Why we write it in the tensor of the rho E? You can call it environment. You can call it Eve system, because this is a pure state. After you perform a measurement on the pure state, so the pure state is always decoupled with the environment. So that's the idea, and then you can reach the final key. Okay, so that's the key idea of the low-Charles. Of course, they assume that there's a quantum error correction, bits and the phase error quantum error correction, and then low-Charles take one step ahead, say that's okay. We can choose this quantum error correction smartly. In their paper, they use the CSS code, such that we can change the order of the final measurement, ZZ key measurement, and the quantum error correction, this operation. So essentially we have computational based measurement. Before that, we have quantum error correction operations. If we can exchange these 2 operations, we can replace this quantum error correction with classical post-processing. Bit error correction becomes a regular error correction. Phase error correction becomes a private implication. And the final key rate will be 1 minus h of the bit errors, 1 minus h of the phase errors. So this part is for bit error correction. This part is for phase error correction. So this is what we get like 20 years ago, okay, for error correction. And then what's the measurement device independent quantum key distribution? Why in the last 10 years people focus on this type of QKD? It's really becomes a because of the site information. So the previous this low charge short price secure, this kind of secure proof is very nice. It's almost perfect, but there's some problem. One big problem is that here we assume that everything is we are working on 2 qubits. But in general, what do we have in the quantum cryptography is that it's a big system. It's not really just 1 qubit. We have lots of side information. We have lots of other dimensions of the system. So, for example, the timing of the pulse, the frequency of the pulse might reveal the key information about this quantum key distribution. And also we have the source problem, like for example, we have multiple sources, multiple source photon sources. It's like for example, when we send out Alice Bob, when they do the communication, Alice might send out more than 1 qubit. Okay. And also we have the loopholes in the detection. Okay. So in general, source is a relatively simple component. So especially with the development of the decoy state, we can take care of it. It's quite nicely, but detection is quite complicated. If you go to the market, if you try to purchase a QKD system, you will see that for a big QKD system, the main price of the QKD system come from the detection, single photon detector. It's quite complicated, and also it's very expensive. And then we have lots of loopholes. And the main loophole lies in the detection loophole. There are many detection there are many attacks targeting on the detection loopholes. And fortunately, we have we call the so-called GRP security analysis. So if the deviation of your realistic system is not that far away, the deviation from the ideal model is not too big. So basically, it's still close. Then we can still reach a secure key. Okay, so that's the idea. So I won't go into details. I just give you the idea that this is GLP. It's try to take care of that. If your system is slightly deviates from the ideal model, how can you deal with it? And then I will give you this part. Okay. So as we explained, it's like in the QKD, in the original QKD, is that the detection the system is very complicated. You might have some loopholes. Source is relatively simple, especially with the help of the decoy state. We can more or less we can solve it. Okay, let's go back to this BBM92. This the entanglement protocol we just introduced. The key point is that when Alice Bob do this quantum error correction, they don't really trust what kind of qubit pairs they choose. They receive. So basically, it can be arbitrary. So in this picture, they don't really trust the source, but they do trust their detection. Okay, so that means that they have a chart. That means that they are in the we call the untrusted source scenario. Security does not rely on implementation of the source. So basically, no matter what kind of a source you put into the protocol, as long as Alice Bob eventually reach some secure key, it is secure. It is secure. So you don't really need to trust the source. You can think of it's a source self-testing or source device independent. Okay. So if the source is scrambled, okay, there's some flaws in the source, Alice Bob will detect it. Okay, there will be X or Z errors. Okay, and also in this protocol, Alice Bob's position, they are symmetric. So normally we call the Alice sender, Bob's is the receiver, but in this picture, actually they are symmetric. It's just sender is in the middle, untrusted sender in the middle, sender to Alice Bob. Alice Bob's operation, they are symmetric, interchangeable. Their roles are interchangeable. Okay, but the detection devices are trusted. The problem is that at that time, detection devices are most problematic, but the source device, they are more or less okay. So the idea is that can we reverse this trust part? Can we trust the sources, but we don't trust the detection part? So that's the MDI-QKD. So the idea that we take the time reversed version of a BBM92. Instead of you have a source in the middle, send the signal, send the integral source in the middle, send to Alice Bob. You ask Alice Bob to prepare state, single qubit state, sent to the middle, and then in the middle, the measurement device will project the state into BIOS state. So from the time reverse point of view, it is it kind of there's some similarity here. And of course, the security proof is slightly different, but we can follow essentially the same security proof idea to prove the security for this MDI QED. Okay, we can also have this phase encoding MDI QED. Why I'm talking about the phase encoding? Because later on we will use this one. So basically, like how do you prepare the qubit? So you separate the optical pulse into two, and then you modulate one of the pulse. The other pulse serves as a reference pulse, and then send two in the middle. And then this is a BIOS state. Essentially, it's a BIOS state measurement. So basically, it's like you interfere the signals at the above, interfere the references, and then you check out the detection result. Okay. From this picture, we can already see that this red part is not really useful because here you don't encode anything. This reference pulse, you don't encode anything. So later on, we'll see that the actual in practice, we can really remove this part. Okay, we can only send out this part. Okay, but I will leave it here. And then there were lots of experimental demonstrations of the MDI QED. So that was like 2013, 2014. So it's a very active research field. Okay, features of the MDI again. So it becomes MDI. So basically, we just reverse the charge part of the device, and then now we trust the source, which is reasonably it's a reasonable assumption, but we don't trust the measurement device. So it will be automatically immune to all detection attacks. Okay, but the performance is still O eta. Eta is the transmitter from Alice to Bob, Okay, so why that is the case? Okay, let me go back to this picture. So the transmitter from Alice to the middle is square root of eta. Bob to middle is square root of eta. And then because for the reference pulse to click, you have a probability of a square root of eta to have a click. And then for signal pulse, you also have a square root of eta for a click. But for this BSM measurement, we need one click here, one click here. So it's a square root of eta times square root of eta. Essentially, you get eta. So eventually, the key rate is the O eta. That's what we can reach. Okay. Keep in mind that eta normally is a very small number because it's exponential. It has an exponential decay with the transmission distance. So we also have a linear bound for point-to-point QPD. If you at least send a pulse to Bob, so how much key you can reach is the when eta is small, then it's bounded by O eta. So we can see that it's already reached the upper bound. Okay, how can we go beyond that? So one way to do that, we put memories. Without memories, we can use we call the optical repeaters. So basically, we need to put the repeaters in between so that we can break this linear bound. What about without these complicated repeaters? The answer is still yes. So this twin field MDI QED. Okay, and then we prove it in the phase matching MDI QED. We prove that such kind of go over this O eta bound is possible if you put the measurement in the middle. Okay, I will quickly go into the details of the go into these protocols. Again, let's look at this protocol. Okay, let's look at the protocol because this part has no encoding from Alice and Bob. We can remove it, just replace it with this part. Okay, so that's the phase matching MDI QED. Okay, just Alice encoded, Bob encoded, do the interference. Okay, I will skip the security proof for this one. It turns out that's because we only need one click, so we can reach the O square root of eta key rate. So eventually we reach the O square root of eta key rate. Okay, what's the catch? Okay, it's so we can see that's this kind of so previously why we need this looks like a reference pulse. It's kind of useless pulses. Why we need that? Actually, we need it for a reason. Okay. So here's the security, here's the performance. Okay, I will come back to this point. Okay, so this if we look at this performance, we can see that this is a linear bound. So the this slope of this phase matching QKD, this protocols, we can see this is slope is okay, because it's negative. I would call it smaller. But if we take an absolute value, it's bigger. So if we take an absolute value, it's bigger. So basically, it's like the slope is smaller than this linear bound. Okay, keep in mind that this is a log scale. This is a log scale. This is a log scale. So when the slope is smaller, so that means that this is linear. Actually, this is quadratic. This is quadratic. Okay. All right. So we can go beyond the linear bound. Because we put a measurement site in the middle. Okay, there are lots of experimental demonstrations. So the experiment is extremely challenging. The key point is they come back to the original question: why we need these reference pulses in the first place? The key point that's because we need to stabilize the pulses. So for this encoding, we require Alice's pulse and Bob's pulse, Alice and Bob signals. Hang on a second. I feel there's something wrong. Oh, okay, it's still here. So Alice, Bob signals, they need to maintain the phase, stabilize the phase for long distance. So basically, we know that's the phase change very, very fast, rapidly. The frequency is very, very high, right? It's extremely high. So we can see that any small drift of the optical length will cause a big phase drift. So basically, the drift cannot be longer than 200 nanometers. Keep in mind that we're talking about hundreds of kilometers of the fiber. You cannot allow the fiber drifts of the 200 nanometers. Okay, so that's why we have to put lots of extra techniques to make this happen. Okay, so all those this type of, we call the one mode MBIQD, it's extremely hard for experiment. Okay, we need to lock the phase. We need to lock the phase nicely. Okay, so there seems a trade-off between the practicality and the performance. So we can see that's so in order to reach this O square root eta, you have to put additional, we call the global phase locking. We have to put this kind of extra technique to do that. So the question is can we remove this very challenge global phase locking? The answer is yes. So that's we use we compare the one mode and the two mode encoding. So one mode encoding, the good thing about one mode encoding, I only detect one signal. The good thing about two mode encoding is that it encoded in the relative phase of very close by pulses. So it's very easy to stabilize it. Okay, so can we take it both? The idea is we send a pulse, we do the ID encoding, and then send a pulse in the middle, Charlie, for the encoding, for the detection. And then you have a single clicks, 1 click, 2 clicks, 3 clicks. Originally, for the two mode, you have to pair these two together. If one of them is missing, then you have to throw it away. Only when both of them click, you can make it work. Okay, so that's two mode encoding. That's why the efficiency is very, very low. We know that's most likely we do not have two adjacent clicks, right? So the idea of mode pairing is that we can pair two clicks together, but they are not adjacent. So as long as you have a one click, you wait for next click, and then probably they are not that far away. As long as they are not that far away, then we can still pair them together as similar to the phase matching. That's kind of an MBIQD. Okay. And then it turns out that we can, with this mode pairing, okay, you just pair different clicks, single clicks together, you can still reach this quadratic key rate improvement. Okay. So recently we have excellent demonstration with the USTC group, and the work is recently will appear in the PIL. Okay. So the conclusion is that we can reach the quadratic key rate, and then we can remove the global phase locking requirements. And in the future, we're still working for can we even further increase the key rate and further enhance the security? Okay, or we can even go to the continuous variable high dimensional encoding case. Okay, that's all. Thank you. Questions?
Okay, very nice talk. Thank you. Do you have questions from either online or in the audience? Okay, we have one question.
Yes, very interesting and exciting talk. Can I ask, recently actually Professor Long actually in Tsinghua University also proposed another, quantum communication system called quantum security directed communication. So okay. What is different between QKD and QSDC? Yeah.
Oh, okay.
QSDC. Okay. And could you make some comparison between those two things
okay.
and their future?
Okay. Yes, it's quite different. It's a very nice question. So it's rather different. Here, I really need to emphasize that, okay? So for quantum key distribution, actually, what we really distribute is the key. Key is essentially it's a random bit. So basically, what we do in QKD is really you distribute random bits to Alice Bob. So Alice Bob will share a random bit, but it is random. For this deterministic transmission, is that you can transfer information directly, but there's a drawback. If you think about it as Alice and Bob, so we have two parties, Alice and Bob. So how can we work with QKD? It's like first you distribute the key, and then you send the information with one pad. So you check the key is secure. After you make sure that Alice Bob can be sure that the key is secure, they will do this information transmission. Okay, so that's the difference in the direct communication. In direct communication, so you still have this checking this idea in between, checking this idea. Alice Bob, they still need to check whether the quantum signal is a quantum channel is okay, but still they directly send out the signal. So normally in cryptography, that's bad, because even if you catch there's some say that okay there's some eavesdropping, your information still already gets lost. Okay, so that's one difference. Another thing is that they use the quantum channel twice for one communication. So Alice Bob, essentially is that Alice Bob will send a signal first, send this quantum signal first, go through the Alice, send a signal to Bob first. So this is through quantum channel, and then go back from Bob, go back to Charlie, go back to Alice. Because as we can see in this talk, is that then you go forward, that loss, that transmittance is eta, and come back is another eta. So this key rate will be O eta square. We spend a lot of time to increase this key rate, but in this protocol, the performance will be automatically quadratically worse than the regular QKD. So that's two key disadvantage to use deterministic key transmission, information transmission with the quantum means. Okay, so in practice, normally it's not very in realistic scenarios, it's not very practical. I hope that answers your question.
Okay, thank you.
Okay, thank you very much. Due to the time constraint, if you still have questions, you can exit offline, and we will communicating with our speakers. Okay, thank you again, Xiongfeng. Hope to see you soon.
Thank you. Yeah.